Simmer it down. I've got to do some housekeeping, but firstly I just want to say thank you very much indeed for spending the time this evening to come and enjoy what hopefully, and I'm sure it will be, a wonderful lecture from Willem. Before I introduce him, I've got to do the mundane stuff, so bear with me. So we're not planning on having a fire tonight. However, should and if we hear an alarm, we have got a genuine problem we need to deal with, so we will escort you out of the building and assemble at the front. And providing you've all come on by the Eventbrite page, we should have a list of names so we can make sure who's here and who's not here, and we'll see how the problem is. So hopefully that isn't going to happen, but I have to do it. Should and if you need to take a comfort break, we have facilities literally just outside of the door. You turn a right, around sort of past the bay window, into the corridor, as if you're going back the way you came in, and the toilets are on the right-hand side there. If you need to go, don't make a song and dance. The lights will be dimmed. You can stealth away and stealth back in. No one will even know you've left the room, so it'll all be fine. Afterwards, so for those of you who've come quite a long way, because I know we've got a real cross-section of students, people potentially joining as students, motor clubs and such like. So for external visitors, afterwards we can go back over to the NCME Centre, which will take you over and we'll do a little bit of a tour. And we'll show you some of the simulators being used, and potentially you can have a go on those as well. So there's a bit of an opportunity for you to have a bit of a look around.
Absolutely worth going over and having a look.
That's all he's come for, really, to be honest. So without further ado, tonight's main event is Willem Toet. He's our visiting professor. His background is unprecedented. I won't steal his thunder. I'll let him tell you himself what he's done. At the very end, I've got the roaming mic. I'm not going to talk on it, but I'm going to pass it around. If you've got any questions, your opportunities at the end, seize the opportunity while you've got the professor in the room. Thanks very much. Over to you, Willem.
Thank you. So I'm going to have a slightly slow start. So I've spent the last couple of days taking 250 slides and movies and things that I wanted to show, and I've had to reduce them because I'm thinking about an hour and a bit, and then time for questions. One slide a minute, pretty fast really. So yeah. I'm going to start slow though, because there are some students hopefully coming who finish lectures now and will be busily on their way. I'm really glad that I've got one of these wearable mics, because you'll soon figure out I cannot stand or sit still. Now, okay, I hit the button. I think I've got the nervous shakes on the button as well. I did just hit it. I'm going to go over here. So I also do some work for the Sauber group. Sauber make the Alfa Romeo Formula One cars. Gives me a little bit of contact with people directly in Formula One. And Sauber also do customer work, so using Formula One tools to develop anything someone's interested in. We've done lots of work, aeroplane-related work, all sorts of work we've done. If you've got a difficult project and you want some serious help, we're there. So this is a 2022 Formula One car-ish. It's a pressure distribution. Pressure, how hard is the air pushing, or how not hard is the air pushing on the surface. In aerodynamics, people talk a lot about pressure coefficients, and they talk about positive and negative pressure. There's not actually any negative pressure, but there are negative pressure coefficients. So if you take the air away and you have a vacuum, you have zero, you don't get less than zero. But compared to atmospheric pressure, you can get negative pressure. It's a relative thing. A number of teams, when they launched their cars the last few years, have done a digital launch. And when they've done their digital launch, perhaps the students out there in the world have been brighter than, or more aware of the special tools that one has access to than the IT departments in the Formula One teams. And a number of teams have had their the shape of the cars, let's say, hacked. And you can understand the technical departments will never release to the marketing people the real Formula One car without modification. So in the Aero group at the Sauber company, Alfa Romeo team, the head of Aero design will always stretch this, delete that, thicken that, move this before it goes, say, a model to be made for manufacture for a toy. And you sort of have to do that. You can imagine if you've got 1 millimetre thick parts on a full-scale Formula One car. You scale that for a toy, it's unmanufacturable. So partly it's that, and partly it's just to make sure that the really important underside is not representative. Nonetheless, it's a vehicle that is pretty much legal for Formula One and a lot better than you could do if you created your own. And so a bright lad in Australia who's ex-Formula One, Kyle Forster, he has a YouTube channel, Kyle Engineers, lots of really interesting videos about aerodynamics, does his own CFD, and he's done his own CFD. He says, Willem, I don't know how much you want to show because you know it's really low quality. I just did it to get an idea. But I can't show you real stuff. This is the best that I can do. And so the color scheme gives you the very high pressure down to very low pressure. And on the underside, you've got a peak of low pressure there, and what you're looking for really is you're looking for the difference in the color, that view to understand how much downforce you've got. But mathematics is fantastic. And so you just create what we call CPZ. So in the Z direction, you just have a coefficient of pressure and you convert it so that whether it's above or it's below, it tells you what's the difference in pressure between atmospheric pressure. And so if you have anything that is blue on the blue scale, then that is creating downforce. Anything that is yellow and red is actually creating lift. So you're creating a little bit of lift in this area where you've got these three turning vanes, vortex generators, whatever you want to call them. But overall, even though you lose here, that creates a change in flow that is beneficial overall. And then this plot is CPX, so that tells you the drag, or CPD, drag. That tells you where you're creating drag. So there's not a lot happening on the top surface, there's not a lot happening on the underside. It's all happening really in front and rear view. And for an aerodynamicist to plot like this, now you would look at this on a much higher resolution screen. This has simulated oil flow on it, and off-body, there's a simulation of what's happening with flow rotation, with vortices. And that's the sort of thing that we would be looking at in great detail and probably in many, many slices going through the car. And a vortex occupies a circular space. It's round. And so depending upon the size of the volume you have, in the past in Formula One we had a flat floor with a diffuser and we had lots of strakes in the diffuser and each one would have a vortex inside it that would be doing some work. But that was because you had a fairly wide, shallow area and you had the space to put a number of small vortices. Whereas the exit of this is quite big and you've got room for, in the end, you've got room really for one big vortex. So you can see games are being played, a little bit of air is being let in there to create a second vortex, and these three all add up to create one big powerful vortex that's strong enough to make its way all the way down the car. And this is slicing through the car, looking at the pressure coefficient. So red would be high pressure, blue is low pressure, and you can see this vortex going underneath the floor of the car that's very, very powerful and tracks all the way back. So this is stuff in Formula One. Outside of the Aero group, nobody sees this stuff. And I reason it's not the real car. The rules have changed already for next year. And nothing I'm showing here would teach a junior aerodynamicist who's got a job in Formula One anything, but it's interesting for people who are not in that position. Now, I'm going to go back now and talk a little bit about some fundamentals of aerodynamics. It would be nice if aerodynamics was simple, but then you wouldn't have a big aero department in a Formula One team. You wouldn't need a big aero department in a Formula One team. Aerodynamics is really complicated. It's just made up of molecules. We are in atmosphere, and there are kilometers of air molecules, oxygen, nitrogen. So nitrogen's the biggest, then oxygen, carbon dioxide, water, and then lots of little ones, helium, hydrogen, xenon. There are lots of other gases in very small numbers out there. And air pressure increases as you come down. And by the time you get down to sea level, the air pressure is about 10 tons per square meter. So a bit more than a yard for us oldies, yeah, square. If you have a vacuum one side and the other side is normal atmospheric pressure, 10 tons. So if we're trying to generate 2 or 3 tons on a race car, we only have to generate less than 10% of a vacuum. So you have less than 10% of the molecules hitting the surface, and you're going to generate huge forces. And that's why the aero groups in Formula One are so big, because you can make such a difference. And there are a huge number of molecules in the air. 26 quintillion, and I've written it out so because the 26 quintillion in like, it depends how big your finger is, but like the tip of an average finger is probably going to be a cubic centimeter. 26 quintillion, that's a lot of molecules. Now, not only that, those molecules are actually a long way apart relative to their size. And that's what's actually quite special about aerodynamics. And it was a botanist who was a really keen microscope user, Robert Brown, 1827. He was looking at pollen particles in water under a microscope, and they were just sort of jiggling around, which he couldn't understand because it's just in still water. And it was Einstein 80 years later, and it was one of Einstein's first, if you like, contributions to science. He postulated, he suggested that it was water molecules hitting the pollen particles that was causing this random motion. And in those days, it wasn't understood. We didn't know how big molecules were. We didn't understand that. And this lower simulation is carefully scaled helium molecules in air, let's say, or in as a gas. So helium molecules, they're about 2,000 times closer together than they would be if they were at atmospheric pressure. And they've been slowed down so the simulation looks so you can actually see what's going on. They've been slowed down about 2 trillion fold so you can see the motion. So this Brownian motion is staggeringly fast. And this is what makes aerodynamics so, if you like, challenging, fun. And different, you can just imagine if we're having a bouncing match. I'm only a little fella. So if you come against a sumo wrestler and I run like hell and bounce, he's probably not going to move very much when I bounce off him. And the same happens with molecules. The heavier molecules have more kinetic energy, and when, say, a hydrogen molecule bounces off them, it gets thrown further than the other molecules. So each mass of molecule will have an average velocity distribution. And if you look at the distribution and then you look, where is the speed of sound? Well, the speed of sound is at about 1,247 kilometers an hour, 775 miles an hour, or 346 meters per second. We always, in aerodynamics, we tend to talk in meters per second. It doesn't sound much, 304, but it's quite a few miles an hour, yeah. And that's, if you look your average molecules, the majority of molecules are nitrogen and oxygen, so they're traveling faster than the speed of sound. But there's about 200 molecular diameters between the average interaction between molecules. So you can imagine, and what is sound? So sound, or what do you hear in your ears, ignoring the microphones and speakers, but if we imagine we turn those off and I'm talking, I'm moving molecules in my throat. That vibration travels through the air at the speed of sound, and you hear it. So at the back of the room, you can hear me speaking at 346 meters per second. There's probably, I don't know, 10 meters back here, something like that. So it's not many seconds, not many decimals of a second, yeah? So it's really fast, and that can tell you that there can be a great deal of mixing within the air, which is one of the next things that makes it deliciously complicated. And then the velocity of molecules in the air is, if you like, a measure of temperature. So scientists will talk in terms of absolute temperature. 273 minus 273.15 or 16 is degrees C is absolute zero. At absolute zero, all the molecular motion stops. We can't get to absolute zero, but we can get so close that the molecular movement is so slow that we know that yes, at zero it will be stopped. The molecules don't move. In space, you're not far away, depending if you're in the shade of the sun or that sort of thing. And then as temperature increases, the molecular velocities increase. And so when, say, the space shuttle comes back into atmosphere, or a rocket comes back into atmosphere, the rocket is traveling fast but in space. Everything else is stationary. When the space shuttle, the ship comes back into the atmosphere, what it sees is gas that, as far as its velocity is concerned, is mega hot. Both are cold, if you're stationary with the atmosphere or if you're stationary with the rocket. But when the two meet, that relative velocity means you've got massive heat. So I'm going to get now very quickly into a few laws of physics. Aerodynamic forces increase with the square of speed. Why the square of speed? So if you're traveling at a certain speed, you're interacting with, let's say, parcels of air. Let's not go molecular size because they're jiggling around so fast you can't do anything with them. But let's go, let's say, a millimeter squared. If you go as big as a millimeter squared, there's like a low-pass filter, if you like, between every scale within aerodynamics. So you go from your molecular scale up to, say, a millimeter squared. That's huge numbers of order of magnitude. The air can be effectively very still. So you punch through at a certain speed, you will interact with a certain number of parcels of air, and with each one you will exchange a certain amount of force. Then you go twice as fast, you're going to interact with twice as many particles, but every interaction is going to be twice as hard, exchange twice the force. 10 times the speed, and you'll interact with, in the same time frame, you'll interact with 10 times the number of parcels of air, exchanging each time 10 times the force. There's your square law. That's the simplest way I can think of explaining it. Probably the most famous equation, if you like, in aerodynamics is the Bernoulli equation. Bernoulli, another human, observing airflow and aerodynamics, he thought that the pressure acting on a surface was the result of molecules impacting with the surface, and that is what happens. And so you can sort of imagine, if you slow everything down a little bit, you can sort of imagine what might happen, say, on the back end of a car, where you've deflected air away. On the back end of a car, when it's punching through the air, you're likely to have fewer interactions on the rear surface of the car. That sort of thing is relatively intuitive. The Bernoulli equation is not necessarily so intuitive. The whole equation, and we only use part of it, so pressure energy, kinetic energy, and potential energy are the same along any streamline of motion. So if you follow an air path, the maths says, the laws of physics say that all the energies available have to add up to the same value. And we quite often will ignore the potential energy term, which is just the density times the gravitational coefficient times the height. So the formula is pressure energy, how much pressure is there? Kinetic energy, half the density times the velocity squared. and then the potential energy, the density times the gravitational constant times the height, those have to be the same in any 2 points along a streamline. And if you're not changing height dramatically, then you can ignore the potential energy and really you're getting quite accurate answers. And that is what we do. But how do you get an intuitive feel, if you like, for the Bernoulli equation or effect? So it has to be along a streamline. Now the key is Bernoulli observed high velocity near a surface, low pressure on the surface. But the shape of the surface is important. So the velocity would be along a streamline. So here on the left-hand side, I've got the coefficient of pressure. Purple is a low pressure coefficient. Red is a high pressure coefficient. So anything beyond the grey, the green, yellow, red is higher pressure than standard. And over here on the right, I have the velocity magnitude. Purple is virtually stationary. Effectively, what you're doing if the wing's going through the air is being dragged along with the wing. And where you have low pressure, you have high velocity magnitude. And this test is being done at 50 meters a second, and the highest velocities get close to double that, fairly close to the wing. Fairly close, not on the wing, but very close. But the important thing to remember is that you've got to measure the pressure on the surface, in other words, at 90 degrees to the direction of flow. So this is my oversimplified explanation of the Bernoulli equation or the Bernoulli principle. So you can derive the Bernoulli equation, and most of the equations that we use in aerodynamics can be derived, and I do teach deriving. For some people it's like, oh, I think I'll fall asleep, because it's heavy mathematics, but you can derive the very long equations that we use in aerodynamics from first principles, just using very simple laws like Newton's, say, second and third laws. So Newton's laws are to do with heavier objects need more force, an object won't change direction or velocity unless a force is applied, that sort of thing. Where a force is applied, you get an opposite reaction. Simple laws that we all understand have been well proven. You can use those, but that's not going to give you the feeling. So for me, the explanation I use that helped me to get the right feeling is interactions with the body and the air around it change the average velocity distribution of the molecules. So we're not getting into a supersonic aircraft punching through and changing the velocity of the molecules dramatically, but the fact that you can get this fast, distant exchange between energies within the flow mean that the leading edge of an aerofoil or a car, the leading edge of a body, will interact with the flow, and you're going to, instead of having the pressure acting the same in all directions, you're aligning more of the molecules in the direction of flow, and therefore less of them are interacting at 90 degrees and touching on the surface. And for me, that's the Bernoulli principle. Now, we brought back ground effect this year in Formula One, so I thought I'd better mention what's ground effect. I'll get into a little bit of the cars first, and then we do a little bit of a play with science. So Colin Chapman's people came up with ground effect and evolved it, and they quite quickly learnt that they needed to try to seal their side pods. Their side pods looked like an aircraft wing upside down, and if you have a narrow wing, like the width of a Formula One side pod, maybe, I don't know, 18 inches wide or something like that, and you have it open on both sides, air can just come in and do whatever it wants, and it's going to be very difficult to get a significant pressure difference between your aerodynamic surface and the outside world if the outside world can just come in. So we've used, for example, end plates on wings in motorsport effectively what they do is they make the wing think in a way that it's much wider, and therefore the flow stays just two-dimensional, and you can get quite a big pressure difference between the upper surface and the lower surface. The wing tip of an aeroplane, there's much less pressure difference on the upper and lower surfaces because they don't have an end plate, and in fact a number of wings now on aircraft have started to develop. Okay, they're kinked, which wouldn't work in motorsport, because in motorsport we always have a maximum width, don't we? And you want the maximum power out of the width you've got, so you just go poof, to the end and bang. So at first, I'm going to use this button, it's easier. And at first they started with brushes and then hinges and all sorts of things, and all the teams ended up with effectively a really narrow little containing box and then a sliding skirt, and they all settled on a ceramic rubbing strip, because you can get ceramics, even then you could get ceramics that basically didn't wear away. People would try a Teflon strip first, and a Teflon's nice and slippery, which is good. Ceramic's pretty slippery too, but the ceramic didn't wear, so the skirts would last a little bit longer. And we're very lucky that here at the university, Bob Fernley, who's a university graduate, he's a doctor, has formed the Fernley Foundation, and together with Jonathan Kendrick, he runs Rocket. You see Rocket sponsorship on a number of Formula teams, including some Formula One cars. Both started life, and I'm the same, started life in what you might call an underprivileged background. Let's say my dad died when I was 6. I left home at 16 because I got put in to be an apprentice, and I thought I'd rather give myself more options. And then 16, I'm on my own, and I've got to figure out how to educate myself, how to survive, live, earn money, everything. Yeah. So I absolutely love the fact that there are people out there who are willing to try and help those who maybe don't have a standard chance, and I'm all for it. So anyway, we have available to us 2 of these cars. One is being raced and prepared by staff, students and help. It's got to race without the skirts, is prepared, you can imagine it's a Formula One car. It's the easiest generation to work on, but it's a Formula One car. They're worth a lot of money, and they're not simple, and so you can't let the students loose on their own, but with supervision, they're able to learn and do a great deal, which is utterly fantastic. And this car is a winner. It races in historic races, and it's a winner. Had a double win at Silverstone last year, the year before, 21. But of course, we also want to do a little bit of science. So with help from a company called Evolution Measurements, who supply a lot of pressure equipment, pressure measurement equipment to Formula One, they have these little stick-on discs. They're a bit over 1 millimeter thick, and you stick them on the surface, and you do get a little bit of a ripple in the airflow around them, but we're able, so here are the little discs taped in place, and aluminium tape, then you rub it down as smooth as you can, and you try and make sure that the pressure tapping tubings that you use to connect to them are running in the direction of the airflow. And they supplied us with 256 pressure sensors and all the kit that you needed to measure it, and we went and did a truckload of testing with that on the car. So you can imagine there is some aerodynamic disturbance, but you get a bucket load of data. Then students, staff and commercial helpers, the company who supplied the Faro arm, and a company who are professionals at doing scanning, but also with student help, student and staff help, the car was scanned inside and out. From the scan, CAD was created. So once you have the scan, so now we have the CAD, because where do you get the CAD of a 1970s, 80s Formula One car? It's all on paper, and you have to recreate it, and you have to know how it was done three-dimensionally. And I learned to create 3D shapes from 2D drawings when I joined the Tolman Group team in 1985, and for me it was a baptism of fire, because it's not necessarily easy. It's a skill where you have to have physical capability to you make a load of slices and put them together, and you have to work out how to wash between. And I had the help of a really good pattern maker who taught me the skills to do that. But nowadays it's all on computers, so you need the same level of skill, just a different type of skill. You have to do it all on computer. And what was fantastic, I think, about creating the car in this way is that it's a warts and all, if you like, aerodynamic surface. Instead of having the perfect design surface that the engineer had in mind, it's what's really been built for the car. So if you look at a few images that come up here, you can see on the side panels there's some ripples, you can see fixings. This is real stuff. Is that me? Don't think it's me. Phones on silent, please. Well, I have had it before where I'm in the middle of giving a lecture here at the university. I'm in the middle of giving a lecture to class with the students, and my nephew rings up. Oops. And he was persistent too. So this is just an unbelievable opportunity. So we've had the CAD of the car. So we've now done CFD runs of the car, computational fluid dynamics, computer simulation of airflow, like doing a wind tunnel in a computer. Computer simulation tools get better and better and better every year. I was actually on holiday in Australia about a year ago, and I would log on to the computers doing this simulation work, and I realized that the computers were completely empty one weekend, and I just went mad and just submitted a load of cases and then apologized to the commercial person whose computer we were doing afterwards. We did a bit of a deal, and I managed to get a pretty complete aerodynamic map. So on the vertical scale on each plot, you have rear ride height. On the horizontal scale, you have front ride height. And then in each little box, each little bubble is a parameter. So on the top, you've got downforce versus front and rear ride height. Then you've got drag. You've then got percentage front, aerodynamic balance. How much of your downforce is on the front wheels? What percentage is on the front wheels? And then car efficiency. And then there's a point there that was ding, alarm bells. And that is at 0 front, 0 rear. That is a car on the ground. Now, it's never going to run on the ground. This car didn't have particular problems. This is without skirts because this is how we're going to race it, or how we do race it. But for me, this is an alarm point. And we'll get to why it's an alarm point. So we can see various trends. You can see that you want to be, if you want downforce from your floor, or total, because the floor is dominant in terms of downforce. If you want downforce, you want to be low on the rear, and you also want to be a bit low on the front up until you get to 0. So even 5.5, your maximum downforce is actually at 5.5, but you've got another good point over there. So the front ride height is a really dominant one. And I forgot to mention, so this car with skirts would probably have had a porpoising problem because it'll come a little bit earlier. And it was the racing driver Mario Andretti who was the first one driving the Lotus to use the phrase porpoising. He's seen dolphins and porpoises, and the car's porpoising. So we did some runs. I only did 3 runs with the skirt fitted onto the car. And at one of the ride heights at 50-50, so it's quite a relatively high, 2 inches, 50 mil front, 50 mil rear, lowest point to the ground. There is quite a difference in the pressure distribution, not on the front wing, not on the front of the wheels, back of the wheels, then the whole of the floor area, and then the rest. You can actually see there's a negative effect on the rear wing because the floor is working better, but that's... And you can also see that, for example, this is a downforce generating area, but you're getting some lift around the front wheels and a little bit of lift around the rear wheels as well. That's pretty standard for an open-wheeled car. So then we get a pressure distribution. Above is the baseline case, below is with the skirts fitted. And if you look at the top surface pressures, it's quite hard to see a difference really between the top surface. By the way, if you really want to look in great detail at something like this and you want to plot where do I see differences, you just take a grid, a whole load of vertical and horizontal lines in exactly the same position relative to the car on two cases, and then you look square by square within your grid, and then you can really zoom in, and that's what we do. Yeah. We wouldn't look at just a picture like this, it's too generic. But the difference between the pressures on the underside is so dramatic as far as I'm concerned. There you have a reasonable amount of low pressure, but here you've just got another world of low pressure. You see it as well in, so these are plots that are quite interesting to see. This is called an X-ray plot. You just look all the way through all the surfaces of the car and add up all the pressures, and you just see in this location of the car, do I have downforce or do I have lift? You can do the same with drag as well. And this one looks at flow rotation, vorticity, and then if it has a vortex, it colors the vortex by how much energy there is in the flow. So you've actually got some vortices coming off the leading edge of the sliding skirt in this case, but you've got vortices coming in further back on that one, which do quite a bit of damage to the flow. So here I'm looking at the three different heights with, so in this case I've got the no skirts on the left and the with skirts on the right. So you can see this is actually a little bit more consistent with right height. It does, the forces do change, but it's more consistent than that one. And then I thought, okay, why don't we do a bit of a plot of the breakdown of drag and downforce. What I've done is I've taken three baseline cases, averaged the numbers on the three, and then three of the test cases with skirt, and just looked at the average of the baseline and the average of the with skirt. And when you look at the drag numbers, you can see front wings only got a tiny bit, front suspension and wheels got quite a bit, the body has quite a bit, the driver has negative drag, so that means the driver's helmet's actually being pushed forward by the flow. It's not the first time I've seen that. Engine bay has some drag, other bits, coolers and so on have some drag. The floor has some drag, a bit more than the front wing, not as much as, say, front suspension and wheels, nowhere near as much as rear suspension and wheels, and nowhere near as much as the rear wing. And then whole car, all added up together. And then we look at downforce, and then suddenly, so instead of it being there's nothing in it, you look at downforce, and there's like one item's changed dramatically, and that's the floor. And what's curious is, so you look at your rear wing, there's a pretty subtle difference on the rear wing, almost nothing. And you would have to say pretty much dominating the difference is the force on the floor. And the average force difference over the three ride heights is about, you get about 57% more downforce just by adding those little bits, bridging the gap to the ground. Monstrous. Now from here, because the skirts in the ground effect era made so much difference, people talk often in the press, motoring press, TV, they'll talk often about using airflow to seal, say, a floor to the ground. That is absolutely not what we do, and I'll explain a little bit later what we do. The other thing that I wanted to mention here, and the biggest, at the highest ride height, where it's very easy for air to get under the floor if it's at a high ride height without skirts, at the highest ride height, you got a 74% gain in car downforce. Huge, just huge. If you could do that on a car today, you'd be an absolute hero. They'd be paying you millions. Yeah. And so I'm hoping that there's someone out there bright enough to invent the next, yeah? Because every generation learn from the generations before and make their next steps, and we've done that. We've made our steps. But there's always more to learn and more to gain. Now, one of the things, I've worked many years as a head of aerodynamics in a Formula One team, And I started with just very few people in my group and ended up with about 100 people in the group. If you've got 100 people working in a group, with most of this lecture theatre in a group, am I going to do any aerodynamics? I haven't got time to do aerodynamics. I've got to manage people who really know what they're doing the aerodynamics. Yeah. And so for me, it's really great fun to understand that role of managing people, but also then to try and how do I give guidance to my people who will know the details more than me? Well, one of the things that I do is I will look for how much energy passes out the back of the car and we're doing nothing with it. And then, in 2008 at BMW, we had what we called a Tomcat, and they were like cow's horns on the nose of the 2008 BMW Sauber. And they rolled up a vortex that took air that would normally pass between the upper and lower wing and would move it to a place where you could get the lower wing working on it, and then you waste a bit of energy creating a vortex, and then you generate a load more downforce, and rear downforce is hard to create. And if you create downforce on the rear wing, that will make the floor work better. These things are, I'm talking here, you can hear it over there, a wing is going to interact with the floor, and they do. But I will look at things like that. Is energy passing out the back of the car? And I will also look at what is the efficiency of the different items that we've got. So for example, the efficiency of the rear wing is between the two cases 3.79, 3.72. Very similar. It's pretty good actually for a rear wing. I've seen a lot worse in Formula One high downforce rear wings. The front wing has an efficiency of 8.3 to 8.32 with the two averages of the two types of car. And the floor has an efficiency 11.9 and 20.2. So for the last 25, 30 years, depending upon what the rules were, I've been pushing my people, get the floor more air, make the floor work harder, because that's your most efficient device. You make that more powerful, you make the car more efficient. So if you like, taking an overview, that's about as much detail as I can get into, which is very boring. Now, what is ground effect? So if you take a wing in free stream, it's just in the middle of air, and you change its angle step by step, you'll be able to see that the pressure distribution around it will change. You can see the airflow lines. You can see that the airflow is being bent by the presence of the wing. I've got varifocal glasses, but that's definitely not a straight line at the bottom. Yeah, and so you can see the pressure distribution and the velocity magnitude, and as the angle changes, you also see a little bit of stalled flow coming towards the end. And what's really curious is that maximum angle I go to, which is 16 degrees on this particular design of flap, it still hasn't reached maximum force, even though you've got some recirculation on the trailing edge. Aerodynamics is deliciously complicated. Then if you take the same wing, I just pick an average angle, 6 degrees, and we then take the ground up towards the wing. You can see similar changes happening, and you can see you're forcing the flow to be straight. Then I searched what I did was run these cases, then I searched for the two cases, runs, one in free stream, one close to the ground, where I had a very similar amount of downforce. And these are 12 degrees, 6 degrees. They generate the same amount of downforce approximately. Now, to understand ground effect, or to understand wings, to measure what the forces are, you will have around a wing, you will have skin friction drag, so you'll have a certain amount of drag because the air is dragging along the surface to a certain extent, or close to the surface. And you will have form drag, which is you integrate, you add up the pressure acting on all little parts of the surface, and you can divide it up. I've done this before, for example, on a helmet, to measure the force on a helmet when we were in desperate trouble, 1989. Johnny Herbert was in the car, little fella, had a bad accident in Formula 3000, was struggling, especially late on in races. He'd broken his foot so badly that he was struggling to apply enough pressure to the brake pedal, so he was an easy target for people to overtake. And so Flavio Briatore decided he'd put someone else in the car, and he contacted Emanuele Pirro. Emanuele Pirro is over 6 foot, or about 6 foot. And that's very tall for a Formula One driver. The cars are better placed now to take people of different sizes, but in those days they were built for jockeys. And poor old Emanuele was absolutely. I got a phone call from Rory Byrne, who was my boss. Rory's a chief designer, technical director of Benetton, Ferrari, chief designer mainly. And he said, look, Emanuele is really struggling, and he says he's being choked at high speed. We need to do something. So we happened to be in the wind tunnel. We weren't even in the wind tunnel 24 hours. We had like 1 week in the wind tunnel, 3 weeks out. It was something like that in 1989, but we happened to be in the wind tunnel, and while they were in parallel testing on the racetrack. So I took a helmet, drilled 32 holes in it, and connected the 32 holes to little tubes of plastic and connected to them what is called a water manometer. A water manometer is just a bank of tubes of water, usually coloured, and you have a big tank of water at one end, and you connect your pressures to the other. And if you got high pressure, the high pressure will push on the column of water until the gravitational force that's pushing back up, because you've pushed water down until the tube balance, it'll move. And if you've got low pressure, it'll suck the tube. There's a mechanical pressure sensor, if you like. Really, really reliable, really accurate. And so we did 32, and so I just associated with each part of the helmet, 1/32 of one half of a helmet, with each part I said, right, there's the vector direction, and that's the amount of area I'll pretend that pressure acts on this area, added them all up together. And in this case, I added them up, did my calculations, what speed is he running? Okay, he will have 5 kilos of lift. That's quite a lot. And I thought, no, I've used half a helmet. He'll have 10 kilos of lift. So you imagine 10 kilos, it's actually around your throat, which is quite delicate. So the poor bloke was really struggling. So then we had to quickly do some work and find some solutions. Anyway, we found some solutions, and they were like, put a foam strip at the back of the helmet to trip the flow and stop it circulating around the helmet. He, Nelson Piquet, other drivers after them, they all wear little flick-ups now. But in those days, they were just like, you are kidding me, that's never going to work. And then you put it on, and it actually works. And wow, this is a black art. It's really odd science. But anyway, but the trick of adding up the pressures works. But if you simplify your wing, just to get a feel for what we're doing, let's simplify the wing to a straight line. Yeah, because on average, it's going to be somewhere in there. Then the pressures acting in that straight line will have a certain vector that's pulling you backwards. The pressures acting on an average of that straight line will have a much smaller vector pulling backwards. That, for me, is the benefit of ground effect. And we didn't invent ground effect, by the way. Birds invented ground effect. Swans, big geese, big heavy birds, they have to basically start flying close to the surface. So they start on the water, close to the surface flying, and so ground effect works in both directions. Aeroplane landing, aeroplane takeoff works in both directions. So they banned the skirts first, then a few years later they banned ground effect floors, and we had to go to flat floor with a diffuser, so we just started work. Of course, we expected this is inferior science, but we're going to do it anyway because we're going to make a difference. And the truth is, it didn't take us very long at all, and we've ended up being able to pass the power of a full ground effect car. So to tell you, I've looked at the data, and I've asked permission to tell you the difference, but I've been told no. So all I can tell you is, in round figures, a current Formula One car will have a very similar level of drag to the ensign, and will have about double the downforce. Last year's Formula One cars, and say 2020 were probably pretty much a peak, pretty much I'd say would have had about 2.5 times the downforce of that ensign, even though you don't have ground bridging devices. We've just used different science to find a better way. So I wanted to understand, right, what's the science behind a diffuser? So with working with a university, and when I was at BAR and Honda, simple bluff body with a diffuser, working in ground effect, scientific studies, and we ended up being able to plot with different angles of diffuser. You end up with a very similar amount of performance with lots of different diffuser angles, but each one has a peak at a different height. And the best performing is actually the steepest one, has a fairly wide area where it's flat. and low-angle ones never achieve peak performance. So, for example, this 5-degree diffuser never achieve, even if you can put it on the ground, it still doesn't achieve maximum performance. But they all fall over at a certain point. Yeah. So if we pick one, when you take your bluff body with a diffuser and you have a certain performance and you start to bring it down, as you bring it down, the coefficient of lift, the aerodynamic downforce increases. Then it sort of slows down the rate of increase, and then at a certain point it will just fall off a cliff almost. Now, people have surmised there are these steps in aerodynamics, but what very few people talk about is the fact that on your way down, you keep, let's say, the good flow on your way down until eventually the air doesn't hang on anymore and it lets go. But it's such a big change to the airflow that you've got to, the car's got to come up quite a way until it reattaches again and gives you the good power again. So that is the cause, if you like, of porpoising. It's the fact you get the step, but the stall and the recovery happen at different points. So you get a stall and then you've got to wait for the recovery, and then in the meantime the car starts to get pushed back up on its springs, then it reattaches, it creates downforce again, gets sucked back down on its springs, and that's the boom, boom. There's porpoising. And that's, yeah, hysteresis. And up until 2022, up until last year, we didn't have this problem because we had a plank underneath the car. We had a relatively narrow reference plane right down the bottom. Then we had a step plane 50 mil higher than the reference plane plus the 10 mil plank. So we had a minimum of 60 mil of air going to the floor of the car, the diffuser of the car all the time, and with then a relatively limited angle on the diffuser, not much expansion on the diffuser, we never were able to get to that point. Yeah. And in fact, you could take the rake of the car all the way up. Yeah. Brake the whole car to try and, actually the rake of the whole car was not about aero power, it was actually about aerodynamic balance, but maybe we'll see how we go for time. And then the airflow patterns that you get, so flow visualization paint is a really nice way to look at what is the flow very close to the surface doing. And in the area where you're getting an increase, it's very early on, the car's very high up, you're getting a little bit of a gentle increase in force as you go, then you're getting a very smooth, controllable pattern. You do get some visibility of the vortices. And the maximum downforce area, type B, but in the maximum downforce area, you get flow on a bluff body diffuser, a simple one like this, you get flow that looks like this. It looks quite complicated, and it looks like it's already let go, but it hasn't. And then at a certain point, one of the two vortices will burst, and that's the point where you get the cliff in performance. And so I think it's also quite intuitive that if you get this sudden drop or this sudden change in airflow, where you get one vortex burst, the other becomes dominant, it sends the flow all the way over here. You've got to get quite a big change in conditions before you revert back to the other flow type. Now, up to and including 2021, we were using all sorts of tricks to try to get more downforce. That meant we had a wake behind the cars that was dragging a load of air along, but the wake was very wide. It was a lot wider. So there's the wake of the front of the car. We're punching a load of air outwards, and by punching, so you can imagine if we take the air that's about to come inboard of the front wheels, and we punch a load of it out, some air's got to rotate in to replace it. And we used that trick, punching the air out, to rotate air in and go under our floor. And that was a trick we used, but it had the consequence of making a wake behind the car that was just massive. And that wake stayed really wide, and that's what made overtaking particularly difficult. So Formula One management then got to work a few years ago. They created quite a small team. In my opinion, they don't have enough resource to do this job properly. I don't know how many people they had, but listening to what they've said, I'm guessing they had 15 people in their aero group, very smart people doing a really sensible job, wind tunnel testing and doing computational fluid dynamics with third-party providers. They did wind tunnel testing at the Sauber facility, where they manage the facility. We don't go in, they manage the facility. They're doing everything themselves. We just provide a 55 million pound wind tunnel, and they go in and turn it on and drive it. We have operators driving it for them, but they control what is done, and we don't even see the data. They take everything away. And so they did a program in the wind tunnel plus a lot of computational fluid dynamics, and they came up with their design. Part of it was styled, so they'd style people working along with aerodynamicists, so they're interested in not only the look, not only the performance, but also the look. And they very happily released a load of videos of what the car was, so I've taken stills from their videos that they've released into the public domain, so I'm happy that I can show this stuff because it's all in the public domain. You need to know how to find it, but it's all in the public domain. So quite a different looking car to what we've had in the past. Now, an interesting thing for me is within the regulation, so the way the rules have been communicated now is a little different in that the rules are communicated in CAD files. And so thanks to a student and race car engineering, this is one of the images they created, which shows you can have the surface of your floor somewhere between these two yellow lines, but you've got a low point here. And after this low point, you actually have quite a long and extensive expansion. And you sort of see, looking at images of the cars, you can see that in some of the floors. So occasionally people will be generous enough to leave their floor exposed where a photographer can get a good shot of it. And so then you can see quite a lot. And there's our porpoising, which is, so another reason why porpoising was hard for the teams to find, and you can imagine as a driver, it's not high G, but that can't be doing his neck any good, yeah? But also this year, or last year, they eliminated the rotary dampers that we used to have, the inerters that we used to eliminate a natural frequency of the car's oscillation. So you got the tyre bounce, you have the aerodynamic cores initially, and then as the mechanical tools we used to use to fight it have been partly taken away. I want to introduce very quickly another law of aerodynamics. We have what we call a no-slip rule in aerodynamics, which I found extremely unintuitive. But when you blow air over a surface, on average, the molecules that would actually interact with the surface are stopped in the flow direction. They'll bounce back up, but they're stopped in the flow direction. And it's not until you get your head round, look at the smoothest surface man can create. What's it made of? Atoms and molecules. So it isn't going to be silky smooth. It's going to look a bit like that. And then what's going to interact? Oxygen molecules, nitrogen molecules. So people will claim to have the smoothest surface in the world, but it's still made of molecules, and most of them are not perfect. And you add to that the electrostatic interactions, molecule to surface, and then on average, and we've validated this with the smoothest surfaces we can find with measurements, the flow effectively is stopped at the surface. Totally unintuitive. That's the best way I can get my head around it. So then you get a boundary layer built up. And a boundary layer starts what we call laminar. So the terms laminar and then transition into turbulent, those terms were created before we knew about Brownian motion, because it makes little sense when you consider Brownian motion. But the flow is, let's say, smoother in a laminar boundary layer, and on a clean surface the flow will start laminar and then eventually will tumble up and start to become more turbulent, where within a turbulent boundary layer you get more mixing, but you effectively the fact that you're stopping molecules on a rough surface in particular will propagate out and give you a boundary layer that's quite thick. A boundary layer, the limit of a boundary layer is randomly, and really it is quite random, it's 99% of free stream velocity is the edge of the boundary layer. And someone had to come up with a number when boundary layers were created. And if you have a laminar boundary layer, it's quite thin. And then you get a turbulent boundary layer will have, depending upon the speed, quite a bit thicker. And a rough surface is going to create a turbulent boundary layer more quickly. Yeah? So you can imagine an old whale with a lot of barnacles on it is not going to have any laminar flow on its tail fin at all. But what's really interesting is the young ones have to wait until they develop barnacles before they can swim as fast as the old ones, and that's because the barnacles on the tail allow them create turbulent flow with all that mixing, water, in this case it's water, but with all that mixing, turbulent flow can handle a pressure gradient, we call it an adverse pressure gradient, can handle that better than laminar flow. Laminar flow will separate catastrophically. And so you need the barnacles for the whale's flipper fin to work. That's just fantastic, isn't it? I just love that. And then the flow around a truck, it's such a bluff body, there's not going to be much laminar there, is there? And the Formula One car, that's a 2016 Formula One car. Yeah, one look. It's pretty out there. And the reason I wanted to talk to you about boundary layers is I surmise, I suggest. Mercedes last year, having won the championship many times with a consistent philosophy of how they do their work. They are a fantastic team. They're a very difficult team to beat. And in a way, for the health of the sport, I'm very glad that they were beaten, because you don't want one winner. So I worked with Michael Schumacher in the Ferrari days when he was winning, yeah, first Benetton, then Ferrari. And the sport does not want one person or one team to win all the time. You need to have a number of different heroes. You need to have a number of different teams competing to be the best. And at Sauber, I can tell you for free, and I don't think I'm giving anything away, we run a rough surface on the belt. And we're trying to simulate the rough surface you get on asphalt. When you go to a racetrack, Pirelli will measure the asphalt for you, and they will give you a macroscopic and a microscopic roughness figure for each circuit, and they might give you different figures for different parts of the circuit. And then the tyre specialists will use that to work out pre-event strategies for what they're going to do with their tyres, and then of course you can do testing to validate. In a wind tunnel, the roughness of the belt will change the way the boundary layer grows on the belt. So the belt and the wind are traveling at the same speed. So you start with no boundary layer because the belt and the wind are just traveling together. But the presence of the car accelerates air underneath the car, and that builds up a boundary layer. So if you have a polished floor, so these are two public domain images that Mercedes have put out there when they're advertising for people and various other marketing things, and you can see that the surface that the belt runs on is shiny. Now, Mercedes are very good at putting some rubbish parts on for test one, that sort of thing, but that's very cheap compared to having to move a belt out of a wind tunnel. The belts are heavy, it takes quite a time to remove them. You wouldn't waste your energy putting a shiny belt on just for the sake of it. And you can see this one, I would imagine this might be a Teflon coating, something like that. And we'll get tyres from Pirelli. And in the past, we didn't have to use, by regulation, Pirelli tyres in the tunnel. And if you were going to a tyre manufacturer to manufacture maybe some special tyres, some tyres that might be simulating a cornering condition, would you go to Pirelli? Well, no, because they're going to supply everybody else, aren't they? So you go to somebody else who's a tyre specialist and you get your special cornering tyres made. You can't do that anymore. But the tyres you run in the wind tunnel, you want them to last a long time. A tyre for a Formula One car will last 200 kilometres. We used to be able to do hundreds of thousands of kilometres in a year in the wind tunnel with our model tyres. And so you can't tear your model tyres to pieces just like you do a race tyre. So we have a way of managing the friction coefficient on our system. But a really good way to manage it is to perhaps use a Teflon coating of your belt, which is smooth, and when you replace the Teflon coating, it's another smooth coating. It doesn't change anything. So that might be one reason why they would use a smooth belt, and it's completely consistent. Our rough belt will wear in the areas where the tyres run. When you replace it, you get a bit of a step in the forces. And with a step in the forces, you then have to do a repeat run. You do a run with the baseline with the old belt. You replace the piece of the belt that's worn, and you get a step in the forces. You have to do a repeat run. You can't make a change to the car at the same time. So you waste a wind tunnel run, which they didn't. But they have too thin a boundary layer, which is then less likely for them to be able to predict the porpoising. They were probably in a position less likely to be able to predict the porpoising than other teams. Now, they also didn't have the best powertrain last year. Yeah? That's also an important factor. But I like that the game gets mixed up every now and then. Now, I don't know whether, I would say the sensible thing might be to open up for questions. I had 250 slides that I was going through, and I've deleted a load. And what I have next is a load of pictures of the cars, looking at details of the cars, maybe mainly to show that they are so different. So Mercedes came up with this really nice trick, and they banned it for next year, unfortunately, because I like clever ideas. But you have areas where you have to have surface and areas where you don't. And this is looking at the front wing end plate from the outside, and they've got this big hole in the front wing end plate where they will actually get a little bit of a jet of air going outwards, and they're starting to create some outwash again, which is exactly what you don't want when you're following. But it's a way for them to get a bit more downforce. It's been banned for next year, but yeah. And you can sort of see through here, see the tarmac through the gap. But I think, why don't we stop there and we get some questions?
Any questions, anybody? I'll wander around with the mic. Don't all be shy.
Yeah, you don't want to be shy. I don't.
Coming up the back. Hold the line, caller.
I'm quite relaxed. Bill, in the meantime, shout.
Just pass that along.
Hang on, wait.
Was there any effect of change from 13-inch wheels to bigger wheels when it came to the porpoising?
Right. Was there any impact going from 13-inch wheels to 18-inch wheels in terms of porpoising? I'd say honestly, no. We would have had probably a worse problem because they eliminated the mass dampers. We probably would have had a worse problem with the balloon tyres because they were literally a low damped spring. It's a damped spring, but it's not got much damping, and the inerters were used to counter the main tyre frequency of vibration. So I'd say probably not. Initial cause, definitely aerodynamics. A normal tool the engineers would have used to fight it wasn't there anymore. I'd say they're the primary things. The big wheels have been really nice for managing tyre temperatures and brake temperatures. We've got space to burn now. It's fantastic.
Yeah. So in relation to the pressure diagram of the side profile of the wing, just how drastic of a difference does a Gurney flap make to the efficiency, the aerodynamic efficiency of a wing?
So I do a whole lecture on Gurney flaps.
Dude, I love Gurney flaps.
A Gurney flap is a 90-degree-ish angle on the end of normally on the end of a wing profile. They are the first part of a Gurney flap is extremely powerful. So at the trailing edge of a wing profile, it's very difficult to get a big difference in pressure, upper surface to lower surface, where you have no distance. So if you have like a pointed end, the pressure above and below at the pointed trailing edge will be much the same. You put a gurney there, and the gurney will allow you to have the distance to get a pressure difference, and also you're stopping the air in motorsport terms on the upper surface, and allowing the air under on the lower surface. You actually get alternating vortices, one following another. So you get the air wrapping around the underside of the trailing edge of a wing element, wraps around the underside and forms a little vortex, and then that meets one that's coming over the top on the others, and they alternate. It's fantastic. Vortices around a bluff body. You can see them in microscopic scales. 2 millimeter diameter tube with air wafted over it, you get vortices coming off, and you get an island, a big island in the Pacific Ocean with clouds going past it, and you'll see if there's a consistent wind with cloud in it, you'll see the clouds going one way and then the other way, and from a satellite you can see the same thing, the same alternating vortices behind big islands. It's weird, and it's got to start with one molecule going one way and one molecule going. It's weird. But yeah, they make a really big difference, and what's really curious is they make a bigger difference to a wing and ground effect. So a front wing and ground effect with a gurney is going to make a bigger difference than a rear wing. And gurneys in motorsport are rule benders. You want more downforce, but the rules don't allow you to go any bigger or longer or higher, and so you put a gurney on, and with very little space you've occupied, you get more power. And I grew up in Australia, and crop dusters, sometimes in Australia, they'll put a gurney flap on a crop duster, and then they can go slower and still stay afloat. They're cool. They're super cool. There's one over here. There's one there, microphone, yeah. We'll come to you.
Just very quickly, in the world of computational fluid dynamics and 100-person sized aerodynamics departments, do you see less chance for a revolutionary new way of looking at aerodynamics, for example, ground effect, because of the amount of computers and the amount of brains looking at the same thing and becoming better at the same thing? You know what I mean?
Yeah, that's, I'd say it is harder with a big department for any one human to come up with the idea that changes the world. But sometimes you go back to using an old idea. The McMurtry fan car. So Brabham built a fan car. You take a great big fan, and the McMurtry came up with a fan car where they've used, let's say, modern knowledge, some good computational fluid dynamics science, and something that's not too aggressive, and they produce an, I mean, I wouldn't call the car pretty, but it's definitely, it stands out. And in terms of performance, off the line, it's like, compared to anything other than a dragster, it's like, whoa, I want one of these. And I think you might find something like that coming into Formula One perhaps in the future. So there is a question over here, Mark, when you're ready. Okay, over here. Yeah, next.
So during the period of time that you've been in F1, what have you personally seen as being a massive and drastic impact within the aerodynamic industry? So what's the most efficient car within aerodynamics that you've seen during the years? So was it like 1980s, or was it
okay.
recent as 2000s?
Okay, what's the most efficient car? So there are lots of things that aerodynamics departments do that maybe make a difference to the world. Yeah. We do some stupid things, like the rules force us to have a limit on how many teraflops we use, so we take certain bits out of computer chips, get them specially made so that they can't do real world work, but they work better for Formula One. That's nuts. That's just nuts, yeah?
I've seen
no, cars, I'm getting there. But also, we do some really interesting things. We write software that allows you with the same compute power to do much more useful computational fluid dynamic work more accurately. All the teams either pay their commercial suppliers or write their own codes. There's some really good jobs in Formula One writing codes that in the end, these codes will end up in the public domain. It might take a while, but some of them, the commercial code suppliers, most of the teams work with commercial code suppliers. They write a better code. They're not going to sit on it for 20 years. You know, you might pay extra money to get them to sit on it for 5, but after a while. And all this stuff is already filtering out. So that, for me, that's a bigger contribution than anything else. The most efficient car is not going to be a Formula One car. It's going to be something like a sports car. Jaguar sports cars so Formula One cars are going to sit generically, without giving anything away to anybody, generically 4-to-1, 5-to-1. I've designed a hill climb car for a mate, and it's sitting 6.5-to-1. But completely different regulations. But sports cars got to 9-to-1 in, say, the silk cut Jaguar days, where the rules allowed them some freedom. And the VW IDR that went to Pikes Peak and set the outright, with an electric car, outright record at Pikes Peak, that's sitting somewhere in the range of 9-to-1. But I've seen cars on the drawing board and worked on cars that are 14, 15-to-1. Now, You talk to an aircraft aerodynamicist and they're going to say, well, it's nothing. We've got wings at 50 to 1, 100 to 1. Yeah? So it depends on the context and what you're trying to achieve. In motorsport, people who are able to do the science, so certainly the Formula One teams and right to the level of, say, Formula 3, anybody who's got a good simulator and good data will be investigating, here is my starting point. What do I want from this starting point? I've got this much power, I've got this much drag, I've got this much aerodynamics, I've got this much tyre grip and so on. What's going to make me do a better lap time? And the Formula One teams will know exactly an average, so on an average racetrack, if we can increase downforce at, say, 2.5 to 1, the cars are sitting at 4 to 5 to 1. But if we can increase downforce at 2.5 to 1, most tracks we're going to go faster. But you use more fuel. And so you've got to balance that at the end of the race. You're going to run out of fuel. And so they balance it for the race where you need a higher efficiency. And anyone so whatever competition you're in, the trick is to understand what you have to achieve to make the category you're competing in more competitive. Yeah?
I've definitely seen a pattern with boats, cars and planes. They've both got a pattern within the F1 kind of criteria. So in regards to the wing and whatnot, it's very, very similar to a wing on a plane. So when I found the pattern with those three kind of aspects, then it's easy to kind of transition into it. What's quite cool.
Yep.
Okay, well, I was going to suggest the gentleman at the front who's got a question. If you do him, I'm going to scurry across the back. Your virtual audience has been sending a load of questions, so I'll read those out when I get back in position over here. So
well,
down
okay,
to the front. Yeah, down to the front.
Yep. Oh, excellent question. Right. I'll repeat the question. So, the question is, with you can get temperature variations on a track, and is there an impact of having hot or cold temperatures on a track relative to the temperature higher up? So I'll give you a few examples. First one is wind tunnel testing. Wind tunnel testing, we started with just a supermarket conveyor belt on steroids. To create a moving belt so that we put our model on and we have a moving belt. And then the belt would lift. So no problem. Put suction, suck it down. We've got heat. Bugger. Okay. And my experience with the heat was before we put cooling under the belt, we were testing at Imperial College in London, and at the beginning of the day, when the belt was cold and the air temperature under the belt was cold, we had fantastic numbers, and at the end of the day, with a hot belt, the numbers were crap, and you were rejecting things you were trying with a hot belt, and then you'd come in the morning and you'd have a step in the data again. So we knew from wind tunnel testing, this is absolutely key. And then you go testing, so another race car example, Ferrari, 95, 96, massive pressure from the bosses, new Aero kit arrives, we do a baseline run, first thing in the morning, it takes 2 hours to change, and then you do your new super duper test parts, 11:30 in the morning, asphalt, 60 degrees. Driver, this is crap. This just doesn't work. Run for a while. Okay, abandon, put the old package back on, let's do another back-to-back. So you abandon, 2.5 hours later, cool of the evening, go back, the baseline's much better than the test part. I wasn't at the test. I was head of Aero there, and I wasn't at the test. And then you look at the results and you think, classic, absolute classic. Okay, we've got to go with 2 cars. And you've got to do, one car's got to be new package, one car's got to be old package, both test in the morning, both get swapped, test at lunchtime, swap back again. And we had to do that before I could convince the drivers and the race engineers that, and so absolutely temperature is critical. You need to understand it. For sure. Very good question. Love it.
Okay, Willem, I've got some online questions here, some nostalgia as well. So 3 people from the virtual audience. Peter B has said, if Mercedes messed up their car, how come in 1994 Williams' team failed to see the leading edge floor stall on their car before the season started. Do you remember that far back?
So how come
So you made the question about porpoising earlier on the Mercedes car, and obviously how it was missed by Mercedes. This gentleman's asking how it was possible in 1994 that Williams, before the season started, hadn't spotted that the leading edge of their floor was going to cause stall on the car in the season.
I wasn't there. I don't know about
your
why.
humble opinion, maybe, or have you not got one?
So 94 was a really difficult but a very interesting year. It's the year Ratzenberger and Senna were killed. Just horrible. I've been in Formula One a while and came from sports cars, and a sports car that I designed the bodywork on flipped at Le Mans, and that's a life-changing experience. The driver scraped away, walked away sort of okay, but you don't want to be hurting people. I'm not in the game to hurt people. And 94 was a particularly challenging year because of that. But what came of it was you see the genuine, honest cooperation between the teams, all the stakeholders, the rule makers, the people making the circuits. The teams will genuinely cooperate when it's safety related, and it's about the only thing where people will put aside their individual needs for their team and their egos, and everything is just, let's make it safer. And so I've also been involved with a car where we didn't spot before the season started that we would have a problem with the floor, and that was the 96 Ferrari. The 96 Ferrari was designed by John Barnard. John Barnard's a really interesting, intellectually really interesting technical director. And he looked at aircraft, and he brings ideas in from various areas, and he looked at aircraft and he saw the separated radiator entries on aircraft and thought, that's logical. You get a boundary layer build up on the side of our body, and so we'll send dirty air into the radiators. We don't want to do that, and he'll separate them. Unfortunately, when you separate them on a race car, you get the dirty air from the tyres come in instead. But anyway, it was a good idea. But he also separated the bottom and put a flat floor on the leading, with effectively quite a sharp leading edge on the start of the 96 Ferrari. And that was being driven by Michael Schumacher and Eddie Irvine. And both noticed that the car was a little bit unstable, and you can imagine a relatively sharp leading edge. In a heavy braking maneuver, you've got a sharp leading edge. You're changing its angle suddenly, and especially when you then start to come up, you've got a sharp leading edge. It's quite likely you'll get a little stall coming off the leading edge, and that takes the velocity of the air distance to travel down the car and send a little shock wave down the car and makes the car a little bit less stable. And Michael Schumacher driving the car was so consistent in the way that he drove the car that he knew what it did, and he drove in a consistent way and could cope with it. Eddie Irvine was a little less precise, a little less metronomic in the way that he drove the car. An inspired driver, and on a good lap, as fast as Shuey and maybe even faster. And we engineered a fix for this problem. It really wasn't until we had the car on the racetrack that we realized, but we engineered a fix for the problem, which was effectively put a little bit of a leading edge radius on this floor. You just take a bit of the front edge of the floor away, and you just replace it with something that looks a bit more like a wing profile. We had to work within the rules. You're only allowed to use radii, but in those days you could get away with having a variable radius and then use a bit of tolerance to anyway. We effectively putting a wing leading edge profile on the leading edge of the floor, and that solved the problem. The average efficiency was the same. And Michael Schumacher's comment about the car was, very nice, Willem, it's easier to drive, but it's not faster, just give me more downforce. And Eddie Irvine went, on average, half a second a lap quicker because it's more consistent. So he would sometimes arrive in the braking zone and brake too early, and then come off the throttle and roll in off throttle, but off the brakes. And the car would then understeer. And if he was still on the brakes when he turned in, you'd have this stall coming off the floor, and the rear end was really light and it'd be completely unstable, and he'd have, whoa, back off. And so that, for me, that was also a really interesting lesson, that some drivers can handle instabilities in a different way. And so, yeah.
Okay, one more virtual question. So JP Race Engineering has asked, during high-speed, high-load corners such as COPs, you can see the Red Bull is visually higher with the ride height. How do you believe the Red Bull were able to produce downforce figures with the car perceptionally looking so high?
Right. So the 22 generation cars, is just, I hope it's 22 he's talking about, but I imagine so.
Yeah, I think so.
The 22 generation cars produce their peak downforce in most cases almost on the where the sides are almost on the ground, and in fact the rule makers allowed us to put stays on to stop the sides of the car flexing down, because you actually do want a little bit of air coming under. And I think when you look at photos, it's very rare to see photos of the cars from underneath. You only see it if people make a mistake in the pits and they have their floor and they expose it accidentally, or you see it when the car's had an accident and some photographer can get underneath and have a look at the car. And the Red Bull have made compromises in the way that they've designed their floor. And I would say probably Ferrari had a higher peak of downforce, but the Red Bull has high downforce over a better range. And once you get to very high speed, you do want some air coming in the side to maintain some rotation in the flow from the sides of the car, not only from the front, but also from the sides of the car. And how Red Bull have achieved keeping the car up when it's got so much force, I don't know. But they've clearly got some good mechanical tricks that they're using to keep the car so that it is in an area where they're generating downforce. And it might be they're sitting it on packers, as simple as that, but I doubt it.
Okay, I'm mindful of time, Willem, so I'll just pick one more. There's quite a few, but probably one that's most relevant is a guy called Thomas Warren. Could you explain what causes the breakdown of the floor edge vortice, and is it a transient behavior?
It's basically not enough space for it. A vortex needs space to be round, and you squeeze it too much near the leading edge and one of them will let go. It's basically that. And the thing about aerodynamics is you can't in an hour explain the complexities. It takes 100 people in an aero group time, a lot of time, to understand it. And remember, with somewhere between 100 and 200 people in each team looking at this problem, basically we all missed it. And I'm really annoyed with my team for missing it, because I've seen it in the past and used to have software traps for when you're getting to that point where you reach the plateau. That's where I'd send off an alarm, but we missed it.
Okay, so that was the virtual questions. Any more questions in the room? Oh, God.
Plenty.
Hands everywhere now.
Right, I'll take this one first because you're right here.
All right. I don't need to get the microphone for that.
Are the changes for 23 substantially different from...
Right, so what are the changes for 23? Are they substantially different? So the kink point has now been forced upwards, and so you get more air under the floors. And there are some other subtle changes, but for me the biggest change is you get some more air under the floors now, and the rule makers are fairly confident that you won't have floors stalling. There's a small loss of downforce, but substantially they're very similar. To be honest, I do worry that the research for the 22 regulations were done by a small group paid by Formula One management, because they're the only people with the money. Now that group have moved to the FIA, which is the correct place for them to be, because the rules need to be written by the rule makers, and the FIA are the rule makers. But under the FIA, it feels to me that there are very few people still doing research for long-term rules. Now, why do I worry about that? I worry about that because each team with, let's say, 100 people, even with the budget cap, the teams with a lot more than 100 people in their aero group, all trying to find a way to create more downforce, less drag, whatever it is, usually more downforce from the regulations. And if you've got 15 people, and I suspect now it's much less, so if you've got an order of magnitude smaller team writing the rules, then every team has circumventing or trying to circumvent the rules or find ways around the rules, then you're going to lose the benefits that the rules have been designed to create, which is better overtaking or better fighting, closer fighting. And we do have a better wake behind these cars. What's been really interesting this year for me is you have less penalty in the corners when you're following. You also have less benefit on the straights when you're following, because the wake now mainly goes up and you dive underneath it, and the wake forms like a teardrop behind the leading car, and comes in nicely, so you get more air to your car. And it's one of the reasons the wings are like at an angle, to just take advantage of that inflow at an angle. Yeah, if you have a question, keep your hand up, keep waving, attract his attention.
I was just going to ask, when the car's being driven at speed, obviously there's going to be a lot more downforce, so it's going to push down on the suspension.
Yep.
Then when you go into the corners, firstly you're going slower, so it's going to lift the car up, and also it might droop one side down.
It does, yeah.
And I was wondering if you look at that when you're doing things like CFD analysis.
Absolutely. So mainly you will look at mapping a car in a wind tunnel. So in a wind tunnel we have extraordinary models. The rules have limited what we can do this year, but we have the ability, virtually all teams will have the ability to move the car up and down. We can pitch it, we can roll it. We can yaw the model relative to the road, and we can also yaw the road. So we can do the road and model opposite directions. We can steer the wheels. You can steer the wheels depending upon what you have in your team. You do all sorts of funny tricks. We can squeeze the tires. We used to have mechanisms. I started in 2006 with mechanisms to distort the sidewall of the tire from internally. So you have a mechanism inside the tire to distort the sidewall to simulate the cornering shape of the tire. All sorts of stuff. The models are works of art. There are some delicious mechanical engineering jobs in an aero group of Formula One, inventing robotic mechanisms that do all sorts of things. They banned us from having our bent models. We're not allowed to bend our model to simulate the fact that when a car's sliding around the track, the angle of attack of the track to the car is different front to rear because the car is sliding. Yeah? So we made a bent model to go in a wind tunnel where the road stays straight, and you just bend the model instead of bending the road. Yeah? They banned it. Unbelievable. So Formula One goes to great lengths, and yes, we absolutely do map the car. But in CFD, you have a limit on compute power, and most teams will tend to do their mapping with a model in the wind tunnel, where in 8 minutes in the tunnel, you can do thousands of combinations of all the parameters that can move. CFD, each one would be an individual run. So you do some for correlation and checking, but you will not do complete mapping. So the number of points I did with the ensign, that would not be normal in Formula One. That's quite excessive. I cheated. I just took advantage of some free compute time.
Would you say that as someone who spends like a lot of time on the development side of Formula One, that kind of the way that F1's moving towards maybe a more driver-focused sort of sport where the cars are very, very close, there's not a lot of difference between the cars now, and the regulations seem to be tighter than ever, because if you look at the 80s and how different all of the cars are, different power units and stuff, would you say that that benefits F1 long-term? He threw me wrong here with all the different parts, but would you say that it benefits F1 long-term to have the cars being quite close in performance, or would you prefer teams to be going out there with more like, I don't know, the WEC, where the cars are completely different and, they all look completely different as well?
Yep. I like, the World Endurance Series has performance targets. I like that. But I do like some engineering freedom, and it is one of the criticisms of the current set of regulations that teams felt there was less scope to make a difference. But just simply the fact that you've got 3 teams near the front performing well and other teams down the back not performing so well, I think there is still a lot of scope to make cars that are faster within those limited regulations. But I also want to see a championship where the best drivers can get to the top, even if they're not necessarily in the top team. Yeah. So I'm torn as an engineer. I want the engineering challenge. I want the freedom, and I would love to have a championship where here's a box, make your car fit in the box, and anything goes. I'd love that. But right now there'd be no human who could drive that car because we have so much knowledge we've accumulated, the cornering speeds you would blank out. So we know from IndyCar in the ovals, the drivers will go at a certain speed around the oval. You go too fast, the blood in the brain starts to go one side, then you lose vision on the eye that's the blood side, because that's connected to the other side of the brain. You start to lose vision in one eye, and you go far enough. If you put yourself in you go into an aircraft type simulator, G simulator, and you sit yourself sideways in there and you spin around, eventually you'll blank out. Well, you don't want drivers falling unconscious racing around a track. So right now, if they just said, build a car, fit a box, make it fit in a box, we couldn't drive it. I'd love to drive it, but we wouldn't be able to drive it. It'd be like playing a computer game, yeah?
There's two on the front here. Let me come.
Yeah, he's probably tried 10 times to put his hand up.
Sorry, have you put your hand up?
Yeah. I can see from here.
Mexico's got a much lower air density, I think, than
it
anywhere
does.
else. Does that have
well,
it obviously has an effect, but does it have the same effect on all the cars, or does it change the playing field?
Oh, okay. Mexico City. Mexico City is at altitude. It's like well over 2,000 meters high. It also is on a bit of a plain. It gets quite hot there. So you get high altitude, less air density, plus it can get really hot, less air density, because the molecules are moving faster. They push one another out the way. So I was one of the first people in Formula One when the circus went back to Mexico City. We'd raced in Mexico City in the past, and people got used to what they needed to do. And we went back there in 1986, and I was with Benetton, and we were back of midfield team. So we used to qualify quite well. We had these magic BMW, really powerful engines, qualified really quite well. And then usually in the race, the engine would let go, and we just didn't have the power anyway in the race. And so we arrived at Mexico City. I'd been writing a lap time simulation code. So I started, how do you write a lap time simulation? Well, you start with, I've got a mass. It's a car. I want to accelerate it. Force equals mass times acceleration. You start with the simplest things, and you just build on that. I just built, and just start with a straight line acceleration, then a simple steady state corner, and then how do I transition between one and the other? How do I do braking? All that stuff. You start mathematically playing. And we got some information, and I used to draw the circuit map. And I got from the circuit map I got from Mexico City, I would draw a racing line and try and simulate the car going around the track. And I got a hint that the atmospheric pressure was low. And I thought, oh, I better simulate that in my code. And I didn't really have a quick way to do it. But we then got chatting as a group. What do you do? And we talked to BMW, and BMW said, oh, yeah, good point. Well, we can take the wastegates off the turbochargers and throw them in the bin, because we'll never get to maximum, so we can save that weight of the wastegates. And then they did some tests on the dyno and realized that, okay, we're going to need very similar cooling to sea level, but we're going to produce a lot less power. And so you want similar cooling, but you've got 75% of the air density. So you've got 75% of the cooling, and then if it happens to be a hot day, you're already in trouble. So we ended up going to Mexico City with special radiators, with basically the sides of the car completely open, almost, and we won the race. My first race win in Formula One. It was like, yeah! And that was because we understood what you needed to do. Now, are there differences between different cars? Different categories of car, yes. But between all the Formula One teams, I'd say they will all need the same thing. They will need better brake cooling and better cooling for everything, but including brakes. And so you go with a special kit normally to Mexico City. And when you look at the louver panels they have on the cars, so I just want to say there is still diversity in the current Formula One teams, because there's all the different front brake ducts of the teams. But okay, a front brake duct. Yeah. And the louvers, I did have a lot of photos, but the louvers you get, so there's one car with different louver arrangement for different events. The louvers are something that we will move this year, and the louvers are located in an area where there would normally be a mild amount of lift, and so by putting the louvers there, you eliminate the lift. So there's quite different solutions on the louvers as well. And so Mexico, you would go open. Yeah, you would go properly open. Not like that.
I'm just mindful of time, Willem. And I don't want to stop you because you are the Duracell. You are the Duracell bunny.
I apologise, we're over time.
No, it's fine. So I was going to suggest, I'm mindful some people have come quite a long way, and I'm mindful you've still got quite a few questions. So I was going to suggest we actually adjourn. Those who've got some questions, don't run off. Willem's hanging around. He's here all night. He's only sleeping local tonight.
I mean,
so
he's maybe stay local.
We press the pause button now, and obviously, for those with questions, see Willem afterwards, because there might even be some virtual questions. The online stuff's gone really well. I'm mindful some of you come quite a long way, and obviously there's some stuff you want to see across the road at the NCME, which obviously we can take some people over and have a look at that now. So if we have like a dual stage approach, so first and foremost, I just want to say thank you all for coming tonight. Hopefully you found it interesting. I know there's been a lot of questions, and I know there's still some more questions to come. I'd like to say to our visiting Prof, Willem, once again, thank you very much. It's been really informative, brought it bang up to date. There's obviously a lot of interest from what's going on currently and how that started 40 years ago with a relic that we have lying in our atrium. But I just want to say, on our behalf, thank you very much, Willem. You can take a bow now. So then I was going to say, just from a housekeeping perspective, if students obviously need to dash, please go. For visitors and guests that have come to have a look around, if you follow me out, I'll lead you across to the NCME. And we can obviously have a look around there and see what Fun and Frolics is going on there. For those of you who've got some questions for Willem, stay back. He'll be at the front. He'll be here as long as you need him. He'll stay all night if he has to do. Unless security throw him out after about 9 o'clock. Thank you, everybody. Enjoy your evening.
Thank you.
I'll get the suit.